So that's the basic idea, and those can be very interesting. We talked about that you need to use linking and brushing if you want to use more, like if you want to see relationships between different axes. So let's take a look at this here again. We've looked at this before. Here I have the scarce data set. I can brush, and then I see these relationships very clearly. It's kind of tricky to see relationships of, let's say, I want to see this item, and kind of like it's almost impossible to trace a particular item, let's say the highest miles per gallon item, to trace it across multiple dimensions. Why is that so difficult? Yeah.
So like one thing, like almost everything is 4 point out, and then from there,
yeah.
Switch.
Yeah, so that's an interesting property of parallel coordinates. You can use them for numerical data, but we can also use them for categories or for, let's say, integer data. So here we have integer cylinders, but the property of that is, of course, that we will not have like lines that go through that area here. They only will go through exactly the 4.0 or 3.0 or 5.0. There is no half cylinder, obviously. And there's techniques that kind of address this a little bit, but essentially that makes it tricky to see for a specific line what goes in here, where does it come out? Yeah.
So I'm sure there are ways you can like reorder your vertical axes here to like get rid of that, right? So like you could put that last to where you can see where all lines are coming from, right? If you only have one.
Yes. Generally, reordering is a very important property in parallel coordinates because you really only can judge well between two neighboring axes. So yes, you could do that, but of course that doesn't solve the problem in general. Let's say I have 5 of these integer dimensions, then that problem isn't solved. But in this case, yes, that would fix that. Oh, and this is actually, at least it says it's reorderable. So here, we could kind of fix that a little bit. But now, yeah. Let me see. So yeah, it basically works for all tabular data types, which is nice about them, including these heterogeneous tables. One problem is, of course, that since I need space between those dimensions, I can only show like a limited number of dimensions. So here I'm showing 500 dimensions, and essentially this is useless, right? This doesn't tell us too much about what is going on here. This is actually the very first visualization technique that I personally implemented ever. This is in OpenGL, I think it was 2007. And I tried to do a parallel coordinates plot. This is with random data, so that's why you see like almost nothing here. And so one thing that you will observe here is that like these parallel coordinate plots, you draw a lot of ink. And so they tend to overplot a lot. So one simple way of dealing with that is to work with transparency. So here I'm showing the same chart with an alpha value for each of those lines. And now I can see the trends. And you can still see this is random data. But you can see the trends in there somehow. So like working with transparency is a solution. Of course, you have to adjust the transparency in some smart way to work for the patterns that you have and work for the number of items. So there's not, you can't say 0.5 transparency works in all cases. Other approaches to address the scalability problem for many items are bundling, clustering, and sampling. Sampling is actually, like if you have a data set like this, sampling is actually quite powerful. And you can do actually just stupid random sampling, and you will still see all of the trends that you have. Like one word of caution though, if you have random sampling and you want then people to essentially draw filters here, let's say I want only the values that are higher than 0.5 or 0.8, let's say, I suddenly have filtered down this data set like a lot. And now I need to like sample again from the original data set, because otherwise I might actually end up with missing items. So once I get into a space where I don't need to sample anymore, I need to also make sure that I show all of the items that are actually in there. So I already mentioned this. We have only correlation between adjacent axes, and one simple solution is to either brush or let users change the order in parallel coordinates. One problem that we have, and we already briefly talked about, is this ambiguity. Like in these two examples here, we don't, because they go through the same point, do we have line A and line B? Does line A continue like horizontally, or does line A go downwards? And so there isn't really great solutions for that. There are some approaches that use curves. So if you have curves, you can essentially see that. But the downside of curves is A, they're computationally a little bit more expensive to render, and if you have a lot of those lines, then it also it doesn't help too much, right? This is like a solution for these small n cases, but it's not really a solution in general. So parallel coordinates show primarily relationships between adjacent axes. They have limited scalability in terms of 50 dimension, 1 to 5,000 records. You have to use transparency of the lines beyond the trivial amount of numbers. The interaction is crucial. We need axis reordering, brushing, and filtering. And in terms of algorithmic support, we can, again, choose which dimensions to show, to choose the order, so optimize the order that we see something interesting, and clustering and aggregation of records. And so let's look at this clustering and aggregation of records. This is a technique that's fairly old, but the idea is pretty smart. This is hierarchical parallel coordinates, and the goal here is to scale up parallel coordinates to really large data set and to address the seclusion problem. And so what they do is they run a clustering algorithm on the data set, and then instead of representing each item here, they only represent the mean of the clusters. And assuming that your clusters are tight, then you can actually represent this data fairly well. And the idea about hierarchical parallel coordinates is that you use a hierarchical clustering algorithm and let the user dynamically choose which kind of level or how many clusters to show. So you can basically imagine you have a dendrogram, and we'll talk more about this in the when we talk about clustering, and you cut that somewhere that leaves you with a discrete number of clusters, and you can dynamically adjust that. And the other thing is they do here, they show the cluster centroid, but also the variation by using this shading. And so by that, you can basically summarize a data set fairly efficiently here and show like this cluster here has this much uncertainty or noise or average deviation, I would say, and we can still use parallel coordinates here. Here's like 6 different plots where this hierarchical parallel coordinate plot slices to different level of the clustering hierarchy. So the first one here is we treat everything as one single cluster. So we have like one median line, so median at every dimension, or mean at every dimension, or whatever they chose here. And then you see there's a lot of noise, right? Because we have those bands, there's a lot of noise. And then we keep increasing the number of clusters. And I think this here is fairly interesting because suddenly we have a cluster that's quite an outlier, that's quite different from everything else. And then here are some extreme cases where you have to like wonder whether this is still useful, right? But generally, this is at least a smart idea, I would say. As a close cousin of the parallel coordinates plot is the star plot. Here, the axes are arranged instead of parallel. They originate from a central origin. And so, what would be like advantages and disadvantages of this technique?
Distinction between different axes. Since we are all the lines are gradient, it is much easier to distinguish.
So you're saying that because all the lines are arranged radially, they're easy to distinguish?
Yeah, I mean, again.
Okay. I don't quite follow. Any other ideas? What could be a pro and con? Yeah.
I don't know. The data is potentially
cyclical, or I can't imagine a situation where that could happen. But that's
Yeah, if you have cyclical data, then you would probably also have more or less like a line chart, right? Because then you would have dimensions that are of the same type, and then it's not really parallel coordinates, but then it's really more of like a line chart around the circle, which is like actually probably not a bad case. So one problem that you have with that is that like you have a lot less space closer to the origin, right? So if you want to draw a line here, it has a lot more pixels. It's much more prominent than a line here, but it's not necessarily that this is like necessarily what you want to do. And so those tend to clutter even more than parallel coordinates. One thing that I kind of like about them is that they produce like this unique shape. And you might actually, there's one brewery in Utah that uses these star plots to show the flavor profile of their beer, right? The hoppiness, the whatever, how bitter it is, and so on. And so this here is actually for flavor profiles of whiskeys. So here you have like a couple of whiskeys from like Old Scotch. I think you have the Artberg, which is kind of an extreme whiskey. You can see it's not sweet at all. It's very smoky. It's very. It has like a high body. It's not too malty. It's nutty. It's not too nutty, and it's not too spicy. And so you can look at those here. But notice that this is a small multiples display. It's not plotting the stuff over each other. So these star plots are usually best used as like one item per star plot. Then they get these like interesting shapes, which have like benefits of being engaging and people like them and so on. But it's not usually suitable to show multiple of those. Yeah, I talked about sampling already. Here is just an example where like these two, like the relationship between these dimensions isn't sampled. This is sampled and this is not sampled. This is from this paper on random sampling. So you can see the effects here. And this paper by Ellis and Dix actually showed that you can actually accurately judge trends if you do sampling like this. Filtering is really about defining criteria to remove data, for example, based on a minimum variability, which is kind of an interesting filter, or the more basic ones are bigger or smaller than a specific value for one dimensions, or you could also do things like consistency and replicates. This can be interactive and combined with sampling. There are also techniques that allow you to filter based on slope. Because sometimes you don't care so much about the absolute values, but you care about the slope between two dimensions. That's called angular brushing. And so you can filter in parallel coordinates based on the slope. So a broader class, or like say a generalization of this, is to create these hybrids. And so this is a paper that takes all of these different axis techniques and generalizes them into basically arbitrary shapes. And so here are kind of like reproduced a couple of published techniques. We have scatterplot matrices, parallel coordinates, a radar chart, a hyperbox, a time wheel, or like a many-to-many parallel coordinates plot. And this is like a paper is called Flexible Linked Axis. And there is a nice implementation of this. So here I have my cars data set, and so I can like have selected the miles per gallon, and I can draw the miles per gallon here. Then I have to like say like let's make it straight. So now we see that there's like a little dot plot of miles per gallon. And now let's assume I want to do displacement, and now I want to place displacement. And now I could say, hey, connect those two. Now I've created a parallel coordinates plot. Now I could add weight, and now I could do something like this, and then say, now show me a scatter plot between those two. And now I have created a hybrid parallel coordinate scatter plot approach. I don't have to do this in a rectangular way. So let's say I want to do acceleration. I can also plot acceleration like this, and then say, hey, show me this with that, and this like skewed scatter plot. And so using this, I can basically create arbitrary complex plots. I can also do these kinds of things in maybe not very sensible ways. Possible, but maybe not smart. And you can move those around if you want. Then we'll update. So this is like a nice way of playing around with the design space of what is possible, and it's a neat implementation. Oh, and they do have some of this curving in here and some of the more advanced features of embedding like histograms or KDEs on these axes. And so people have published on these connected charts. Like here we have from Michael McGuffin's group a system monitor display like for computer servers. And we see things like program usage, GPU temperature, CPU temperature, network usage, and the lines kind of help you understand the related items without having to brush. And then I showed this before when we talked about multiple coordinated views. This is kind of like taking this even one step further, where we don't only use these axis-based techniques, but we also combine them with other charts, including heat maps and basically stacked bar charts and so on. So you can create these complex charts as much as you like. So a special kind of visualization that is dedicated for categorical data are parallel sets with spatial axis orientation. Parallel sets are basically a special version of parallel coordinates to handle categorical data. And in categorical data, I have a discrete data, a small number of values, and no implied ordering between attributes. And so the task here would be to find relationships between attributes, and parallel sets are also an interaction-driven technique. So this data set that we see here is this familiar Titanic data set that we've seen. So we have the class of the patients that they've booked on the ship, and then their sex, and then we have other attributes such whether they survived or not. And so here the first dimension here is the class, and so we see that basically we have these blocks that are proportional to the number of items that are of that category. So we have first, second, third, and crew, and you see that third and crew is about the same, versus first and second are relatively small. Then we look at the distribution, and then we have the second dimension here, female versus male, and then the proportions of each of those in the first row are shown as ribbons connecting to the second row. So we can see that in the first class we have a roughly equal split between female and male. In the third class we have a lot more males than we have females, although overall there's more females in third class than there are in first class. This is a D3 implementation of this technique, and so we can look at the interactive version. So here we have whether they survived or perished, then we have sex, age, and that's only divided by child versus adult, and then class. And so I can hover over any of those segments here, and I see where these people are in the other dimensions very easily, but it wouldn't be too hard to trace them. So one thing to note is that the further down you are from the origin, the more of the splits you get, right? So here we have a lot of fine lines already, because we need to distinguish between all the survived, perished, female, male, child, adult, and class, and so on. So that gets increasingly, let's say, fine-grained as the further we are from the origin. The original technique also had these integrated box plots in these dimensions, but that's like a nice touch, but not particularly important to the technique. So one thing that's important, like since, well, class is maybe ordered, but things like male, female, or other attributes are not ordered, And so by reordering them, we can actually sometimes remove overlap and make the chart a little bit easier to see. And so here we can change order, in this case between crew and third class, to kind of resolve, well, it actually makes it worse, but it would be possible to do that. This technique also allows you to aggregate categories, so you can say first, second, and third together, or crew, so you can dynamically create higher level categories if you want to. And then you can also filter out. So for example, if you if you have like things third and crew, it's quite dominant in this plot here, and so if you want to look at the distribution of first and second class in more detail, you could simply filter out the third class. And then you would be left with a much more detailed representation of the properties of first and second class. And then finally, we have the highlighting option that you can see if you click on any of those blocks. Okay, so that's it about axis ordering techniques. Any questions about that? Generally, I should say that I personally tend to like parallel coordinates with caveats, but there's a lot of people who think they're not great. And so you kind of have to be careful whether to use them or not. I think there's a place for them to show overviews and to show like rough distributions, because they're quite good at that. But if you want to look at details, they're maybe not always the best. There have been user studies though that showed that they're, for example, better to run queries by interactively filtering them than, for example, writing SQL code even by people who are SQL experts. So there are benefits to using these kinds of visualization techniques to run queries. So comments? Well, if not, let's talk a little bit about filling space. And so there's two different space filling approaches here, the dense and space filling approach. And so I don't want to talk too much about these space filling approaches because A, we have talked about them before when we talked about partitioning views. So this is the example with the London properties. And here, like each of these like tiny rectangle corresponds to properties in London. And we can partition them in various ways, and we can arrange them in various ways. But we'll talk more about these techniques when we talk about trees and visualizing trees, because essentially what you need for this is a hierarchical structure behind it. Instead I want to talk about pixel displays. And this DB is one example of that. And so the idea of pixel displays is that each data item or each attribute is an item as a single pixel. And so that's different from heat maps where an item is a row. Like in a heat map, you have an item as a row, and you assume that all of your columns are of the same data type and of the same scale. So we talked about heat maps in the context of, for example, gene expression data, which is kind of like we have always the same data scale, right, and the same data type. Pixel displays are one item per point, and they can also, like these items or these points can contain multiple different dimensions on them. And the benefit of pixel displays is, like for heat maps, is that we can fit a lot of them on the screen. We can basically fit as many items on the screen as there are pixels, on the order of millions. And of course, this relies heavily on color coding as heat maps did before. So the challenge for heat maps, we had the simple layout, a row is an item, a column is a dimension. Now that we don't have that, we have to choose our layout. And so there have been many, many different approaches published about this, like Hilbert curves or spirals or anything like that. And here would be an example for a spiral. There's this, like, you have to worry a little bit about the ordering, as in all the heat map approaches as well. But let me show you a figure. So this is actually now not a single pixel, but each of these blocks is considered a pixel. And so here we're encoding 6 different dimensions for each of these, like, and I'm calling this whole thing here a pixel. And then you start at the center, the most important item according to some function, is placed in the center, and then you arrange them circularly or in any other shape that you consider. This is a paper from '94, and this is the kind of charts that you get from them. So, what are your thoughts about this?
Looks nice.
It looks nice, and you get a lot of color. It looks nice.
It's very hard to understand what it means.
Yeah.
What am I getting from this?
Yeah.
In the center is more.
Exactly. So the arrangement makes it tricky to understand what are the items. The color, especially that you have 6 different dimensions, are tricky to read. And so this is like I basically tell you guys about this for historical completeness, but I haven't seen those in much practical use. So it's a way of thinking about it, and there's neat mathematical properties, but they're not particularly useful in practice. So that wraps up the table lecture. Now I think we have enough time to talk about storytelling.
Do you have an example of one of those using a worker?
I don't have it at hand. I can Google it. Or I'll send something to Slack later. Okay. So storytelling is really an important piece because we talked about the spectrum between exploration and communication, right? And this storytelling is of course on the communication side. So when you're trying to convince somebody of an interesting observation that you've made in your data set, you should use some storytelling approach. And we also really want you to use storytelling in your projects. And so this lecture today will show you all of the different ways that you can tell a story. There's going to be a couple of really cool videos and things to explore today. So I want to start out with the 6-minute video. I think it's just really worth watching it, both for the content, but I don't want to judge the content, but it's really well narrated.
I saw recently that I can't get out of my head. A Harvard business professor and economist asked more than 5,000 Americans how they thought wealth was distributed in the United States. This is what they said they thought it was. Dividing the country into 5 rough groups of the top, bottom, and middle 3 20% groups, they asked people how they thought the wealth in this country was divided. Then he asked them what they thought was the ideal distribution. And 92%, that's at least 9 out of 10 of them, said it should be more like this. In other words, more equitable than they think it is. Now that fact is telling, admittedly, the notion that most Americans know that the system is already skewed unfairly. But what's most interesting to me is the reality compared to our perception. The ideal is as far removed from our perception of reality as the actual distribution is from what we think exists in this country. So ignore the ideal for a moment. Here's what we think it is again. And here is the actual distribution, shockingly skewed. Not only do the bottom 20% and the next 20%, the bottom 40% of Americans barely have any of the wealth. I mean, it's hard to even see them on the chart. But the top 1% has more of the country's wealth than 9 out of 10 Americans believe the entire top 20% should have. Mind-blowing. But let's look at it another way, because I find this chart kind of difficult to wrap my head around. Instead, let's reduce the 311 million Americans to just a representative 100 people. Make it simple. Here they are: teachers, coaches, firefighters, construction workers, engineers, doctors, lawyers, some investment bankers, a CEO, maybe a celebrity or 2. Now let's line them up according to their wealth. Poorest people on the left, wealthiest on the right, just a steady row of folks based on their net worth. We'll color code them like we did before based on which 20% quintile they fall into. Now let's reduce the total wealth of the United States, which was roughly $54 trillion in 2009, to this symbolic pile of cash. And let's distribute it among our 100 Americans. Well, here's socialism, all the wealth of the country distributed equally. We all know that won't work. We need to encourage people to work and work hard to achieve that good old American dream and keep our country moving forward. So, Here's that ideal we asked everyone about. Something like this curve. This isn't too bad. We've got some incentive as the wealthiest folks are now about 10 to 20 times better off than the poorest Americans. But hey, even the poor folks aren't actually poor, since the poverty line has stayed almost entirely off the chart. We have a super healthy middle class with a smooth transition into wealth. And yes, Republicans and Democrats alike chose this curve. 9 out of 10 people, 92%, said this was a nice, ideal distribution of America's wealth. But let's move on. This is what people think America's wealth distribution actually looks like. Not as equitable, clearly, but for me, even this still looks pretty great. Yes, the poorest 20 to 30% are starting to suffer quite a lot compared to the ideal, and the middle class is certainly struggling more than they were, while the rich and wealthy are making roughly 100 times that of the poorest Americans, and about 10 times that of the still healthy middle class. Sadly, this isn't even close to the reality. Here is the actual distribution of wealth in America. The poorest Americans don't even register. They're down to pocket change, and the middle class is barely distinguishable from the poor. In fact, even the rich between the top 10 and 20 percentile are worse off. Only the top 10% are better off. And how much better off? So much better off that the top 2 to 5% are actually off the chart at this scale. And the top 1%, this guy, well, his stack of money stretches 10 times higher than we can show. Here's his stack of cash, restacked, all by itself. This is the top 1% we've been hearing so much about. So much green in his pockets that I have to give him a whole new column of his own because he won't fit on my chart. 1% of America has 40% of all the nation's wealth. The bottom 80%, 8 out of every 10 people, or 80 out of these 100, only has 7% between them. And this has only gotten worse in the last 20 to 30 years. While the richest 1% take home almost a quarter of the national income today, in 1976, they took home only 9%, meaning their share of income has nearly tripled in the last 30 years. The top 1% own half the country's stocks, bonds, and mutual funds. The bottom 50% of Americans own only 0.5% of these investments, which means they aren't investing. They're just scraping by. I'm sure many of these wealthy people have worked very hard for their money, but do you really believe that the CEO is working 380 times harder than his average employee? Not his lowest paid employee, not the janitor, but the average earner in his company. The average worker needs to work more than a month to earn what the CEO makes in 1 hour. We certainly don't have to go all the way to socialism to find something that is fair for hardworking Americans. We don't even have to achieve what most of us consider might be ideal. All we need to do is wake up and realize that the reality in this country is not at all what we think it is. Zone.
So, what do you guys think? Okay, so let's take this apart from the technical concept. So clearly this was highly scripted, right? But notice what they did. They did a lot of annotation. They did a lot of highlighting with synchronized storytelling, really adjusting basically what is shown to what they're saying. And like, we don't expect you to do a video in your project, of course, or we expect you to do a video, but not an interactive video like this. But we will talk about how we can do something like this in the next couple of minutes with like also interactive or even static techniques. Another thing to consider when you tell a story like this is your frame. And you can frame something neutrally, or you can bring in an opinion and the bias. What do you think? Was this a neutral representation or a bias, or an opinionated representation? Okay, I couldn't hear. Opinionated, maybe, most people? So, do you think the data is opinionated?
No.
So what is opinionated? the narrative, yes, and the tone. We had things like the dreaded socialism, like with a sarcastic voice, yeah.
Well, I feel like the data is opinionated also in a way of like occlusion. Like he can also show how much the top 1% of Americans donate, right?
Yes. The other interesting question would be to like wealth, of course, is concentrated in the hands of people that have it, right? Income would be another interesting thing to look at and to contrast. But I think that's kind of like a weakness in being honest that they don't talk about income. So there's many other facets to this, right? And clearly this is not meant to be like a neutral piece.
Is this like their gross or net?
This is in wealth, so things they own. It's not about income. What did you think about like breaking this down to those 100 people compared to the stack bar charts they had initially? Like that's a technique that people use to make stuff more reliable, right? Because it's even though it's exactly the same as using percentages, like having a group of like say 100 people makes it somehow more tangible, and then we can kind of like assign people to classes as they did here. So let me show you another chart or another short video. Well, okay, first, some people have called storytelling to be the world's second oldest profession, and good stories are more than just providing facts and data. It's really important that they situate and give context, and that's what this video did, right? It kind of like talked about what it was like initially, or what people thought it was, what people think is ideal, and then it talked also about some historical context and so on. So they brought in a lot of context and situated it in something that we care about, and they also educate. It's not just about showing data, it's about consciously educating. And the questions that a story like asked is who, what, where, when, why, how. So this is like from basic journalism. These are the questions that you want to ask. And this is like generally, stories should start with an introduction, state a problem, have a climax, have a resolution, and then a conclusion. And this doesn't apply to data storytelling. Today, as I talk about it here, this applies to any story that you want to tell. If you write like a novel, this is kind of like the schema that most novels also follow. So let me show you another story. Here, this is about underscoring your storytelling with data and visualization specifically is underscoring your arguments with data or with facts, and to also leverage the power of visualization to show trends, to show correlations, to show outliers, and to convey magnitudes. And so, who's seen An Inconvenient Truth by Al Gore? Okay, so a couple of you. It's a film, and I'm going to only show you this like chart of CO2 versus temperature correlation that he does in this film.
Compared to what's going on now, there's just no comparison. So if you look at 1,000 years worth of temperature and compare it to 1,000 years of CO2, you can see how closely they fit together. Now, 1,000 years of CO2 in the mountain glaciers, that's one thing. But in Antarctica, they can go back 650,000 years. This, incidentally, is the first time anybody outside of a small group of scientists has seen this image. This is the present day era, and that's the last ice age. Then it goes up. We're going back in time now, 650,000 years. That's the period of warming between the last two ice ages. That's the second and third ice age back, fourth, fifth, sixth, and seventh ice age back. Now, an important point. In all of this time, 650,000 years, the CO2 level has never gone above 300 parts per million. Now, as I said, they can also measure temperature. Here's what the temperature has been on our Earth. Now, one thing that kind of jumps out at you is, well, let me put it this way. If my classmate from the 6th grade that talked about Africa and South America were here, he would say, did they ever fit together? Most ridiculous thing I've ever heard. But they did, of course. And the relationship is actually very complicated, but there is one relationship that is far more powerful than all the others, and it is this. When there is more carbon dioxide, the temperature gets warmer because it traps more heat from the sun inside. In the parts of the United States that contain the modern cities of Cleveland, Detroit, New York, in the northern tier, this is the difference between a nice day and having a mile of ice over your head. Keep that in mind when you look at this fact. Carbon dioxide, having never gone above 300 parts per million, here is where CO2 is now. Way above where it's ever been as far back as this record will measure. Now, if you'll bear with me, I want to really emphasize this point. The crew here has tried to teach me how to use this contraption here. So if I don't kill myself, I'll... It's already right here. Look how far above the natural cycle this is, and we've done that. But ladies and gentlemen, in the next 50 years, really in less than 50 years, it's going to continue to go up. When some of these children who are here are my age, here's what it's going to be in less than 50 years. You've heard of off the charts. Within less than 50 years, it'll be here. There's not a single fact or date or number that's been used to make this up that's in any controversy. The so-called skeptics look at this and they say, so, that seems perfectly okay. Well, again, if on the temperature side, if this much...
Okay, so he's making a really dramatic point with a prop, and so props can be useful. But he also tries to show correlation, right? Something fairly complex to a lay audience here. So I think this is like a fairly convincing story that he tells here. So let's look at this a little bit more formally. The components of a data story. Here is a data story that's in print. This is about baseball in this case, and like what's the story? What is the story about?
Home run record.
The home run record, yes. And more specifically?
Barry Bonds and whether or not he was on steroids to reach that.
Exactly. And you knew that. That is the story in like just a couple of seconds. And why did you know that? Because there was a great title. So the story had a title. So we have an introduction. We're starting out the story. 755 is how many home runs he had in his life. And then steroids are not to pursue this on. And then you can basically drill down more into this story. So here we have context. And the legend. So like every chart where you try to tell a story, like every chart generally should have legends and labels, but especially if you're trying to tell a story, you need to be very careful about your labeling. And so they have like a very simple line chart here. 3 different people, Hank Aaron, Babe Ruth, and Barry Bonds. Barry Bonds being the red line, and then Hank Aaron being the black line, Babe Ruth being the gray line. Okay, so that's context, legend. Then we have the main story here. The main story really is the progression of home runs over these people's careers. So we see essentially the point that they're trying to make here is that we have kind of like an inflection in the performance of this guy. And that inflection of the performance is also annotated of a key point. So they show that there's suddenly a change in trends. And then you probably can't read this, but it says essentially, According to allegations in a book about bonds, he began taking steroids in the 99 season. And that's where his performance suddenly took off. So that's kind of like the key point of this chart, trying to say, hey, it's something like there's an anomaly here that we should look at. Then we have more context, and here they use matching on content. So this is the same, same data, also uses the same color, also uses the same visualization technique, but it does something a little bit different. Instead, by aligning it by season, it now aligns it, and you can't probably see that, by the people's age. And so it turns out that most people's performance as baseball hitters levels off at 34. But not in the case of Bonds. He actually outperformed his previous records after that age. And then there's more context. There's multi-messaging and in-depth information where you can look at other players and then have different paths. And so that's kind of like a well-designed infographics as you could see it in a magazine or in a newspaper. And so like we've now seen like 2 different videos and like a print story. And it turns out that we can actually break down these data stories into a couple and 7 different types and can analyze them like this. So this is from a paper by Siegel and Kerr from 2010, where they break down data stories in these 7 genres: magazine style, annotated chart, partition poster, flow chart, comic strip, slideshow, film, video, animation. And so what are the ones that we've seen so far today?
Film, video.
Yes.
Poster.
And partition posters, yes. Exactly. Those are the 2 that we've seen so far today. Magazine style is essentially, or you could also say like scientific paper style, where you have like a reference in the text and then a figure that floats somewhere around. Annotated chart is really where the visualization is front and center, and we just have pointers to it. Flowcharts are like specific for specific data types, I would say. Comic strips are becoming more commonly used, especially like data comics, and they essentially whereas a partition poster, like we just saw before, like does it impose an order in how you consume it? Not really, right? You might start at the very left, the top left, but it doesn't really impose a reading order. Comics impose a reading order, and that sometimes makes it easier to like tell a story that is like more control. You have more control as a narrator. Then you have slideshows, which like and film, video, animation. I think those are fairly obvious. And then there's this other dimension here: is the story author-driven or reader-driven? And in the case of videos, it's of course highly author-driven. Also for data comics, it tends to be author-driven. And very often you have heavy messaging here, and you don't need interactivity to that. On the opposite spectrum, we have reader-driven stories, where we don't have any ordering, we often don't have messaging, and free interactivity. And so we've seen these 2 stories here, but now we can take a look at this one. So this is like a data story about the path to the White House in the Obama-Romney election. And I think this is one of the most interesting visualizations that the Times has ever done, because it kind of like lets you explore a pretty complex, scenario here. So you basically can like explore options and say look yourself at what happens if Obama wins Florida, if Romney wins Ohio, what are the paths that any of those candidates have to the White House? And so essentially, you can see that in this case, this path is not particularly viable for Romney, so you could conclude that basically Romney would have to win Florida to win the election without, except for a very rare case. So if you assume that Florida goes to the Democrats, then if Obama wins Ohio, then everything else here is already mute. So, and that's kind of like very, very user-driven, right? So here, like I'm in the driver's seat, the visualization kind of like tells me a story because it still narrates, right? It says if Obama wins Ohio, Obama wins. This is like completely automatically generated storytelling in that case. But it doesn't give you a preset option or a preset story. It's completely up to you to build the story yourself. And then so Hare and Siegel also defined these different types of structures. So the Martini glass structure is something where you start with a very narrowly narrated story and then suddenly open up the whole data set for people to explore. So you start at the stem, you kind of like focus the story for a while, and then you let people look at the data in more detail on themselves. So here is an example of the Martini class structure. So here, this is by Periscopic, which is a nonprofit, and that visualization is about gun death. And so first we are in this kind of like, basically a video is playing now, right? So we get like a narration, and we're in this stem part of the Martini glass. This essentially tells us that like how many people were killed in the year 2013 and how many lives, how many years were lost. And each of these lines is a person, and basically it starts at their age 0 and the line ends at the time they were killed. And assumes like an average age of whatever, 75 or 80, whatever the average age is. And so now the kind of like automatic part of the story is over, and I can actually, and this is a little bit hard to see, I guess, for you guys here, I can actually start exploring. For example, I can look now at what are the children in this plot, and now I can see like these are all of the children that were murdered. And so you can see that here the orange basically stops where they died. So now there's other variables that I can facet this by region, I can facet this by time of the year, I can facet this by sex, and so on. All of these options are now available to me. Interactive slideshow is when I split something into multiple scenes and allow interaction midway. And so here is an example about budget forecasts. Yeah, that's it. So here we have this stepper, and essentially the point of this is to compare budget forecasts with reality. So we could basically, there's like President Obama's budget proposal estimates deficit of 1.6 trillion for the current fiscal year and 1.3 trillion in 2011. Then I can go to the next story, and that juxtaposes it with last year's forecast. Like, what did people forecast in the past, and how did it materialize in reality? And so, not surprisingly, it turns out that the forecasts that politicians make don't usually work out that well. And so here are, like, over time, past forecasts. And one thing I find interesting is that all of these past forecasts always look basically just like uphill, right? So you can see those little lines pointing upwards. Sometimes it's not the case, right? So here people have expected a worse economy than it actually was. So this is now the second step. And I can interact now in this slide and look at each of these forecasts in detail. So I am at a stage, at a slide, and can browse this in more detail. And that keeps going on and on. So that's the interactive slideshow example. And then I guess the most difficult thing to implement is the drill down story, where you really let the reader completely decide which path to follow and make all of the path annotated. So that's a little bit like the Obama, like the path to the White House. But in this case here, this is about how this bear market compares. And essentially, you can click on every one of those lines You can click on every one of those lines and you will get like a little story about that. So here, well, there's some context. I was expecting, like, you can see like a little story about each of those lines. So it's completely up to you to explore that. Here's the big recession in 1929 to 32, and you get like stories about each of these different lines. There's no predisposed or pre-planned order in terms of narration. So we talked about this a little bit, but I want to emphasize this again. So the layout principle for storytelling with data is to really use descriptive titles, descriptive subtitles with more text, smaller font, have annotations, and then use saturations. So here are a couple of examples of like a very neutral representation of data and the storytelling presentation. So here we have ice cream flavor preferences based on 2014 survey of elementary school students. And we see a representation of the data without the story that's being told. And here's the alternative where a story is being told. Chocolate was the most popular flavor among elementary students surveyed. You highlight chocolate, you make it clear this is kind of the interesting point. You still have all the data as you had before, right? But if you compare those two stories, the one is actually engaging, the other one is just a dump of data. Here's another example, a descriptive title and the saturation to emphasize a point that you want to make. So you have project results before and after implementation of a grant, and then you have project A, project B, project C. That's one way to show this, before grant funding, after grant funding, and then say, alternatively, project A had the greatest gains after the 4-year grant funding. So, and this is emphasized by giving A color and increased saturation compared to B and C. And so here, from a neutral representation of facts to a very simple data story. Here, like an example of using a descriptive title and descriptive subtitles and annotations to increase understanding. Here we have a number of studies funded per year, and unless I know what this data is, I don't know nothing about this now, right? But on this alternative here, we're funding more studies each year. Beginning in 2013, we set aside new funding to measure the effectiveness of initiatives, and we evaluated 39 of our programs in 2015 alone. And then we have an annotation here that says 2013 new policy introduced, and it kind of highlights an important point that somebody wanted to make about this chart. Interactivity is an important piece here. We talked about steppers before. Scrollytelling or scrolling is an important way. We talked about this when we talked about interactivity. Then playing, forward, rewind, and so on are all possibilities. We have details on demand so that you can provide highlights when desired. But the one thing that is not true for general data visualization, but specific to storytelling, is making it relevant to the reader by asking them questions like, what do you think, or who are you, or where do you live? And I think this is one of the most effective ways of doing these kinds of data stories. So here's the visualization of the record temperature in 2015. So 2015 was the hottest year record, and then we kind of did a visualization on that. So here we see the temperature record of New York City. And like, of course, that's a smart default for the New York Times because many of the readers might be there. And so you see the background. The light gray here is record low. This is record high, and this is like the median, basically average high, average low for those days. And then the red one is 2015. Notice that they have a title, they have a subtitle, they have annotation. They say like record low 2 degrees, a record high 95, record high 97. So they call out all of the new records. But what's really cool about this is that you can put in like your hometown. You can say Salt Lake City. And now you can look at how did that year go in Salt Lake City. And you can see that there is like a couple of months here in June that were extremely warm, but they didn't have a record day. But then there were some record highs in September, October, and beginning of November. And what I really think is super cool about this visualization is that all of the annotation is, of course, not hand-curated, but data-driven. So they created this very customized story just using data by simply like pulling out the records and annotating them automatically. And I think this works actually in 3,116 cities, so that is fairly customizable. Another way of doing this that I really think is a great idea is to ask for opinions and prior knowledge. So ask readers to draw a trend and then juxtapose with two things: A, the reality, and B, what other people think. So here, the New York Times has these like you draw it things. So here we have a chart, percent of children who attend college and parents' income percentile. Okay, and so you see this is like sketchy rendering here. It's meant to be like an approximation, and they ask you to draw what you think the relationship is here. So what should I draw? So some like steep increase is what I'll try. There's a tip, I should go through this point. So let's suppose we'll do something like this, and then say it goes pretty high. Okay, so that's like a reasonable hypothesis, I would say, right? And now I can say I'm done, and now you get this juxtaposed to the reality. And it turns out the reality here is a very linear trend. We made it much more complicated than it is in practice. Essentially, the more your parent make, the more likely you are to go to college without like more complicated functions. But then they also show you how other people did. And so people tend to, like you see here in the background, people tend to underestimate how people from poor families, how frequently they go to college. And they tend to maybe slightly overestimate how, let's say, top 18 percentile children go to college. Here's another example of that, where you can basically, you draw it, what got better or worse during Obama's presidency. And so here we have unemployment rate. And so we know that was 2008, we had the recession, so we probably had an increase in unemployment rate, but then maybe unemployment went down, right? So now you can compare it to what actually it is. And I did this just like an hour ago. So what do you think is number of immigrants convicted of crimes who were deported under Obama? Down? Up?
Increase.
Up. Straight up?
Yes.
So there was a big bump. National spending on healthcare. Up slightly or much?
Slight up.
Maybe around 18.
So it increased, but less than I drew, and so on. So there's others here. There's like the number of troops in Afghanistan and Iraq. Yeah, so these are very engaging, right? It kind of like, it lets you think much more about the data than just showing people. Because like first they ask you to really formulate a hypothesis and then validate your hypothesis, and then you can think about why was I off or why did I actually make it correctly. And so I think that, I don't recall exactly, but there has been a paper that studied that, and don't quote me, but I think they showed that that people remembered much better when they did these kind of drawing things. So a couple of other design considerations. So here's a chart. This is about traffic fatalities in the United States. And fewer people are dying on the US roads, but we have seasonal trends. So we have a couple of charts here. We have every year sees the same peaks and throws and fatalities. Then we have the holidays that stand out. New Year, July 4th, and Christmas. And then here we have a year of basically a time chart for these three holidays from the 80s to 2005. And then we have the, which is part of an overall reduction in fatalities. So we have the overall fatalities in this chart at the bottom. Okay, so this chart, what's good, what's bad about it? So let's start off with this one here.
That's a lot. It's a lot of colors.
Too many, a lot of colors, right? And what is the point of the colors? So clearly, we don't want the colors here. What about this chart?
Pretty solid.
Pretty solid, but I guess we want to tell a story, right? We want to say holidays are a problem. Like people disproportionately die January 1st, Christmas, and July 4th. And so that doesn't really show up well here, right? You can see it. You can see January 1st here, and then you can see July 4th here, and then you can see Christmas here. But we could probably do better. And I guess the problem here is the color scale. And so let's just look at the redesign of those two. So we have, like, if we have fewer colors, averages for context, which is important, better scales and richer annotations, we can redesign this chart like this. So here we have the average of all years in the middle, and then we see like the fatalities in 2009, which is when this was made, and then the fatalities in 1980, when there were 4,000 people in August 1980, and in August 2009 there were only 2,500 people that died. And here, a color scale that is like basically over-dramatizes the effect of the holidays, right? So we have essentially a diverging color scale at the midpoint, and that highlights that in like holiday season generally, when people tend to drive more, and specifically those holidays like January 1st, July 4th, and Christmas, they stick out. And similarly, for the other charts, they are simplified, they are rescaled. They basically, we don't, like here we had a chart that was scaled to 0. Here we have a chart that is not scaled to 0 and has annotations and explains the context of this chart. So very similar charts, just a couple of little subtle tweaks, and makes this from like a not very well designed visualization to a good story, like a good data story. So you probably heard about this CRAP principle for designing: contrast, repetition, alignment, and proximity. And so these are kind of like basic design principles. Contrast is about making elements different to increase understanding. So here, the contrast is between the like highlight, the main element, and the subtext, right? So the contrasts are, in this case, the color, but also the font size. Then we have repetition. So we kind of like know we have 4 items of similar type, these 4 different rules. So they have a similar style. Then we have alignment. So nothing on your chart should be unaligned. You should always align something with something else. That's just like a design rule, and you should always align things that belong together in some meaningful way. And then proximity, and we talked about this, related items belong together, and so that's why there is less space between the header and the subtitle of each of these major items than between those items. And so like just following these very simple principles will make your designs a lot better. So next I want to talk about engagement. So we talked about like neutral versus bias, but generally you need to think about who is your audience. And I think for me this is the hardest time I give a talk, for example, is if I don't know exactly who my audience is. So you will really have to ask yourself the question, what does your audience know? What are their motivations? What experience do you and them share? What are common goals, and what insights can you give them? These questions, like if you know all answers to all of those questions, you will be able to create a much better story or even give a better talk. And so we can kind of like have create this fake chart here between opinionated and neutral in terms of your story, low information density versus high information density. And so like, these are just examples. A board meeting would be fairly neutral and has still low information density. A research group meeting, for example, would have high information density, but would not be opinionated. Like an expert panel at a conference, for example, would probably be opinionated because then it's more fun and can contain high information density. Whereas a TED Talk tend to be very opinionated, right? But they are still fairly low information density. And so here in the middle is where we're supposed to be doing education. So this chart here, clearly from many years ago, because RIM is still the most prevalent platform for smartphones. But what's the target audience here? Marketing agency. Do you need special skills to understand this chart?
No,
No. Is it opinionated?
not really.
Not really. So it's clearly not very opinionated. What about this one here?
More dense.
Yeah, it's more dense. It contains a lot more data. Target audience, general public, or some specialist? Specialist, yes. Then here we have where there's smoke, there's cancer. So this could be general public, but I would say probably like educated, probably in some magazine or some like not necessarily in a scientific journal, but in some like let's say public science journal or something like that. And it's fairly high density. It's not like a ton of data, but fairly high density. Is that very opinionated? Yeah, so clearly, like the target audience here would be the general public, but it clearly has a message, right? So this is not a neutral chart. So here you could do the same chart by like reframing it and saying death on decline, removing the colors, same data, very different charts, right? So if we kind of like split this up here, we have like neutral, low information density, very opinionated, low information density, high information density, and neutral, and then I don't necessarily agree that the cancer one is very opinionated, but you could make an argument that it's more opinionated than the other charts. So just to recall, these were kind of the examples here. And so then I wanted to do an exercise, but I think I'll do this next time since we have only a couple of seconds left. And so I'll see you guys on Tuesday.
Doing okay?
I love it.
You want to check the office right here? Time now.
Yes. Yeah. Just 2 years over with